Hello, my friends. In this video, we are going to talk about complex number, and we need this background information in order to resolve uh, AC circuits impedance, for instance. So, to begin with, let's see what we have learned in high school. Complex number can be expressed in various forms. One of the most simple forms is rectangular coordinates form. So we can say that, right? Complex number uh, uh, rectangular form. Rectangular coordinates. So this means uh, Z is going to be A plus JB. And if you are going to plot the complex number, then we will need a diagram, so-called Argon diagram. And in this example, we have A and JB. A is the real part of the complex number, and B is the imaginary part. And to plot this, we need a diagram, and this diagram is so-called Argon diagram. And in the Argon diagram, we use the horizontal axis to record the view part. So the horizontal axis will be the view part of the complex number, and the vertical axis is the imaginary part. So in this example, we have A as a view part of the complex number. Then we measure from the origin to A horizontally. That much distance, right? The length here is A. And the and we are going to do the same for the imaginary part. And we have B as the imaginary part of the complex number. Then we measure from the origin to the to distance B vertically. And you do a projection, then we end up with a point somewhere between these two axes. And this point is so-called Z. So this is all about the rectangular coordinates representations of a complex number, Z. So is there any other way to express the complex number? The answer is yes. Just like in this example, what we do is, first of all, we join Z to the origin. We draw a line to join these two things. And the length of the hypotenuse here is square root of AB, A square plus B square. because the length here is A, the length here up here is B. And the length of the hypotenuse is usually so-called the absolute value of Z, or the magnitude of Z. And in the Argon diagram, we can extract the absolute value of Z, and also we can also extract the angle. And the angle, according to this diagram, because this is the right angle triangle, and beta will be equals to arc tangents, and then B divided by A. B is the imaginary part of the complex number, and A is the real part of the complex number. So that's what we can get. There are special terminologies for the complex number. Argon diagram is one, and for the module, for the absolute value of Z, we also have a special terminology. We call the absolute value of Z uh, we call this uh, modulus of Z. And theta is so-called argument of Z. Arguments of Z. And then if we have the information of the modulus, and if you have the information of the argument, then that will be enough for another form of another representation of complex number. You just now you have learned the rectangular coordinates form of complex number, and you also need to learn another form. And here, A is going to be the length, hypotenuse, and then times cosine theta. The length here is the modular of Z, and then cos theta. And obviously, B can be calculated in a similar manner, sine omega t. So in other words, if you substitute A and B back to equation 1, A and B back to equation 1. So what are we going to get? We get Z is equal to the absolute value of cos theta, and then the plus J, because you have J term here, and then sine omega term. So we do a little bit of algebraic manipulation, and we end up with Z cos and this form of this is the so-called polar form of Z. So this is so-called polar coordinate. I will just highlight it. Polar form, polar coordinates. Now, we need to continue, yeah, because this is not enough to solve complex number problem. So let's erase the board and then do a summary of what we have learned today. What we have learned today is the rectangular coordinates. And we have also learned the polar coordinates of polar expression of Z. But is it enough? The answer is no. And by our formula, we have another form, cos theta plus j sine theta is actually equals to E stands for the exponential of j to the power e to the power j theta. This is a very important formula. This means you can calculate the right now with this formula. You can also express z according to here, right? It can be modulus of z and then z j theta. This is a very important expression, and this one is so-called exponential form of z. Now, why do we need to learn this property thing? The answer is we need to manipulate complex number, and without Euler theorem, you can't do that. Now, so I'm going to demonstrate to you how to do this. Right? The first thing that we want to do is to do this, right? Z to the power n. What is this? And because you learned our formula before, and this one is not going to be difficult. So it will be a Z, and then E, J, theta, and then bracket it. And then let's see what happened. Let's see what happened. And we got this, and here we will get this. So hang on a minute. We know that by our formula, we can express uh, j to the power j theta as cos theta plus j sine theta. We can do that. So can we do the same, right? Do it in a reverse manner. So this guy is going to be cos, sorry, bracket, cos n theta plus j sine n theta. So this is what we can do for the for z to the power n. And what happens if the modulus of z is 1? Then what do we get? We get this one. And this thing is so-called, now, how about the right side? The right side doesn't have to be expressed in exponential form, right? It can be Zn, and what is Zn? Zn is just the original complex number. So in other words, we can say cos theta plus j sine theta to the power n times is equal to cos n theta and this thing here is called the Morvre theorem. The Morvre theorem. This is the conclusion of the Morvre theorem. And actually, the Morvre theorem is the same as Euler formula. Now, you have already learned how to use the Euler formula, which is the most important formula for this video. And you also managed to prove the Morvre theorem. So we are going to apply what we have learned today to solve the complex number problem. Now suppose Z1, we have two complex numbers. One is Z1, and we have already learned that Z1 can be expressed in polar form. In this case, the angle, the argument of the Z1 is beta 1. The modular is this one, yeah, the absolute value of Z1, yeah. And then we also have another complex number, Z2, and beta 2. And the question is, what is either, what is this? And right now, because you have already learned Euler's theorem, so this one is very easy. So we are going to do it. And we write down the polar form first, and then we write down the polar form of Z2. And now, I think you would agree the angle is going to sum theta 1, the sum of theta 1 and theta 2 together. And now, you have done this, right? Z1 times Z2. But what about Z1 divided by Z2? And again, we are going to use the same thing. Use and we substitute the top and bottom with the original expression, the polar form, right? And we can say that eventually we end up with another polar expression, and the argument of this complex number is going to be theta 1 minus theta 2. So we have already learned the product. And now how about calculus? Calculus of a complex number. Now let's try this. Suppose Z is equal to absolute value, and then E J omega T. So this is a complex number. The argument, right, of Z. So absolute value of Z, right? Modulus of Z is given, and the argument of Z is going to be omega T. And I'm going to integrate Z dt and see what happens. And if we do that, then we will substitute dt. Now, because the absolute value of Z is basically a constant, so we should move the constant out of the integral to make our life easy. And dt, and different people have different way of resolving this equation. For me, I will do this. I will insert j omega here, and then the t will remain. And then here I will do this. So this is the way how I resolve the problem. Eventually, you will get j omega, and we have already defined modulus of z plus e to the power j omega t as z. So the numerator of this expression is going to be V, yeah? And then the bottom one is like this. Yeah, that's simple. So now our integration is done. And how about differentiation? Differentiation is going to be much easier. So let's say, right, we are going to differentiate. Differentiate. And we are going to find dv dt and see what happens. And z is going to be this guy. Again, you need to use train rule. Again, this is high school math. And then dj omega t dt. So if you do that, then the final answer will be z and then j omega and then yeah, e to the j omega t. Yeah. So the answer is very simple. Yeah, you can continue. J omega z. So this is the final answer. Thank you very much. If you have any question, please leave your question to the comment sections. Thank you.